Actually, Parag was very clever by not coming last time. So I made a complete mess, and so I'm going to do it again properly this time. I hope. Okay. So the aim was to prove the Kaplan-Meier density theorem. So let me remind you what the theorem said and what we need to prove. So there's a So remind you what it says is that if A is a unital star algebra, actually I don't even need you don't need unit. It's just star algebra which is SOT dense in a one-Neumann algebra M. Then we want I remind you that the one Neumann density theorem says that A oh no, there's already given as being asserted then. Sorry, no. The Kaplan-Meier says that in fact, let me say that this says that the unit bond of A is SOT dense in the unit bond of M. And to prove that, I said we'll prove in fact that if you take the self-adjoints in A, the SOT closure is the unit bond of the self-adjoints in M. And the Hermitian can be approximated by. So I believe what I did do last time correctly, anyway I'll do it at the end, that from this one can get the general fact fairly easy. Okay. In fact, two assertions that we make, that even, what is? AH, Hermitian. Also that A plus 1 SOT closure equal to M plus. Right. Okay, so the first note that if we write D equals the norm closure, then B is a C star algebra. It may not have identity, I don't care. It is A C star algebra which is SOT dense in M. And what is clear is that A contained in B contained in M. Right? Consequently, it is enough to prove, therefore, without loss of generality, I may assume that A equals B. That is, it is enough to prove the theorem for norm-closed algebras. If I prove that for norm-closed star algebra which is SOT dense somewhere, its unit ball is SOT dense in M. If I prove it for B, if I know that B1 is dense in M1, SOT dense, A1 is actually norm dense in B1. So certainly A1 is SOT dense in M1. So without loss of generality, the A is norm closed. So A is closed under continuous functional calculus. So if we take a self-adjoint in A, I can apply continuous functions in it and I will stay in A and stay in M in particular. Okay. Okay, next observe that SOT convergence implies WOT convergence. That means that if something is WOT closed, it is SOT closed. Right? So I'm saying that if I take the WOT closure, then this is SOT closed, and so it contains, as it contains A clearly, it must contain the SOT closure of A. And since A is a linear space, and for convex sets the SOT continuous and WOT continuous linear functions are the same, for convex sets the being closed in one topology is the same as being closed in the other topology. Consequently, this is actually equal. That is, A is okay. Why I need this is the following thing. I looked at the map. See, the point is that the adjoint mapping is only WOT continuous, it is not SOT continuous. So if you look at the map fx equals x to the x star by 2, then f is WOT continuous. Right? By what we proved, A is WOT dense in M. Because one has assumed that A is SOT dense, and we've shown that the WOT and SOT closures are the same. So A is WOT dense in M. So if I take anything in M, I can approximate it by elements of A in the WOT topology, and since the adjoint is WOT continuous, it follows that AH, which is equal to F of A, is WOT dense in MH. In F of M, which is equal to MH. And hence, by again repeating the same argument, if I look at AH, the same argument applied earlier. See, the point is that I said for any subspace, if it is convex, and so if it is closed in one topology, it will be closed in another topology. Now, AH is a real linear space, and hence it is convex. And so, to say, see, this says that AH WOT closure equal to MH. But AH being a real linear space, being WOT closed, the same as this thing is also equal to the SOT closure. Okay. So, although the adjoint is not SOT continuous, we went through the circuitous way to show that the Hermitian things in A are SOT dense in the Hermitians of M. Okay. Now let us fix an X in. See, what do we want to prove? We want to prove that anything in the unit ball of MH is SOT approximable by elements of the unit ball of AH. Okay. So consider the function. Let me call this capital because I want to use little f again. So consider little f of t equals 2t by 1 plus t squared. So this f is a mapping from minus 1 to 1 to minus 1 to 1. So last time I did by looking at the derivative, showing the derivative is positive in this interval minus 1 1, that this function is strictly monotone increasing, and at minus 1 it is minus 1, at plus 1 it is plus 1. So it is a homeomorphism of this onto itself. Consequently, it has an inverse, right? So there exists G equals F inverse, also continuous. Right. Okay. So what do I want to do? I want to take So let y equal to g of x. Now x was a self-adjoint with spectrum in -1 to 1. So x is in MH1. So the same is true of y. Right? M is a one-dimensional algebra, certainly close to the continuous functional calculus, and things are mapping something in the contraction. X is in the unit ball, and the function is continuous with range in the unit ball. So the image of f is also a contraction. Okay. So so this was one of the exercises I think I gave you, which is that g of f of x equals gf of x. So this means that x will be equal to g of y. Sorry, f of y. F of g, f circle g is identity. So it follows that. So there, what is it? X equals 2t, 2y, 1 plus y squared inverse. See, the functional calculus is home of it. See, this says that 1 plus t squared times x is whatever. 1 plus t squared times what is this? This is going to be 2t. That's what this says. Since one plus t squared x is f of sorry?
F of g is one function. So fy is equal to identity.
Yeah. No. So I've written something wrong. So I want to say x is 2y 1 plus y squared. No, that is I'm saying. I'm saying this is f of y. I'm justifying that this is f of y. F of t is 2t by 1 plus t squared. So f of t is 2t by 1 plus t squared. That means 2t equals 1 plus t squared into f of t. Right? If you apply 2y, 1 plus y square, or I write it the other way, I'll write this on this side. Functions commute. I write this as f of t times 1 plus t squared is 2t. So f of y into 1 plus y squared is twice y, and 1 plus y squared is invertible. Because why this self-adjoint, everything is real. Okay, so this is x. Okay. X is 2y by 1 plus y squared. Okay, now because y is in MH, so it is in MH1. It's in MH1, so it's already in MH. So this implies by the assumed strong, we proved that AH is strongly dense in MH. So we can find the net BI in AH such that BI converges strongly to Y. Okay, now I want to go back. Now x was obtained from y by this rule. So I want to do a similar thing to the bi. So I define ai equals, actually these things, y and 1 plus y squared commute, so it doesn't matter which way you write it. So the 1 plus y squared inverse y and this are the same. So I'll write this as 1 plus bi squared inverse times 2bi. Sorry? bi is self-adjoint, no? bi is self-adjoint, so bi squared is positive, so that plus 1 is invertible. Okay, so what can one say about this AI? BI is, see, notice that because this function f of t for any t, 2t by 1 plus t squared is always less than equal to 1. Right? So that means that norm ai is less than equal to 1. So this belongs to AH1. Since absolute value of 2t by 1 plus t squared less than equal to 1 for all t. Okay, so now let us do some computation. So I want to say that AI converges to x. See, x was, we started with the element x in the unit ball of MH, and I want to get, and I've chosen, obtained elements in the unit ball of AH, and I want to show that AI converges to x. So let us see what the difference is. What is AI minus x? Okay, so what is this? So this is 1 plus bi squared inverse 2bi minus 2yi 1 plus yi squared inverse. So the deliberate reason I am writing things in this way, left and right. See, now b and y need not commute, so I have to be a little careful with what I do. So Now observe that this can be written as, so I throw in here a 1 plus y squared times 1 plus y squared inverse. There is no yi, this is just y. So I throw in a 1 plus y squared, 1 plus y squared inverse here, and I throw in a 1 plus bi squared inverse times 1 plus bi squared over here. Then what I will get is so this is these two things cancel, give me just this, and here I have a 1 plus bi squared inverse. I will throw in a 1 plus bi squared times twice y. Okay, I have just multiplied by 1 written in a clever fashion. Okay. Now this one wants to claim we come to that. So I claim that this is equal to, I'll justify this in a minute. Twice 1 plus bi squared inverse times bi minus y plus bi into y minus bi into y, the whole thing into 1 plus y squared inverse. Let us see why. There's just a little clever arithmetic again. So let us look at the inside first. If you just look at the inside, what do you get? What do you have? Because this inside term is equal to, let me take the bi and the bi y squared here. And as I said, bi times 1 plus y squared and then take the y terms. Minus y minus bi squared y minus 1 plus bi squared y.
Asking, from the asking.
So this is equal to this square bracket. This is equal to this, and then if I put this into this, then you have exactly. Now you compare. So this time this is exactly this first term, twice bi and 1 plus bi squared inverse times 1 plus y squared and the second term is going to be similarly twice what do we say, bi
And we have proved that bi converges to y.
No. So are you convinced of this step? Huh? Okay. So now I want to use this condition to say that bi converges to y. AI converges to x SOT. So what I have going for me is that multiplication is jointly continuous on bounded sets. Right? And there is a 2 which will be helpful. So let's look at the terms separately. So I want to say that both terms converge to 0 strongly. If you look at this, if you apply this to a xi, and y 1 plus y squared inverse is some bounded operator. So that xi y minus bi times this will converge to 0 strongly, and you have a 2 bi 1 plus bi squared inverse, which is a contraction. Right? Consequently, the second term goes to 0 strongly. And the first term similarly will be, this is a bounded operator, bi converges to y, and this is a bounded operator. Right? 1 over 1 plus x squared is always less than or equal to 1. So this thing has norm less than or equal to 2. So this is a bounded net. This is null convergent, so the whole product is null convergent. Similarly, this is a bounded net, twice bi 1 plus bi squared inverse, and this is null convergent, so the whole thing is null convergent. So AI converges to X. And so we proved the self-adjoint assertion. Here the net of self-adjoints in the unit ball of A, which converges strongly to the given contraction X in the unit ball of MH. Very good. Now the positive case is easy because why? I know that multiplication is jointly continuous, and I also already know the self-adjoint assertion. So if I have now given an A in m plus 1, that implies certainly that A to the half is in MH1. But that implies that there exists Bi in AH1 by what we just proved, so that Bi converges to A to the half. Since Bi's are all bounded, again using that multiplication jointly, strongly continuous on bounded sets, we conclude that bi squared is in A plus 1 and bi squared converges to A squared, to A. Right, so very good. So I've got through and the last part. So just for Parag, let me repeat this thing that what we wanted to prove was that the unit ball of A itself was dense in the unit ball of M. We proved something under assuming self-joinedness and positivity and so on. So in general, so that is the thing I was saying last time. If you take M2 of A, which you can think of as sitting inside B of H raised to H, this is a sortie dense, is a star algebra which is a sortie dense in M2 of M. Because you take a matrix in M, Mij, if you can approximate each Mij by Aij in, if you take an M in the unit, if you take an X in M2, M, the unit ball, then you know that let me call this Z. There exists Aij in M2A1 such that this matrix converges to Z. And now you do this matrix trick, but you take Z equals 0 x star. This is what you want to prove. No. Sorry. So this is what you know. H1. I take the Hermitian, I look at M2M, M2A is a sortie dense in M2M. So by what we've proved, that means the unit ball of M2AH is a sortie dense, the unit ball of M2MH. And now you give me any X in the unit ball of M. Then this will be in the unit ball of M2M. This self-adjoint and there will be a contraction. This will have norm less than equal to 1. Why does this have norm less than equal to 1? You do this star this. That will give you X star X, X star. And the norm will be the maximum of those two. And so you will find that has norm less than equal to 1. So this is a contraction. And so you can find Aij converging to this. Implies there exists. So if I just look at the 1-2 entry of this matrix, if I have a whole matrix converging associated to whole matrix, then each entry will converge to the corresponding entry. This will follow that A12, there exists A12 in A1 such that A12 converges associated to X. Okay, so finally we have completed the proof of Kaplanski density, and as I said, the crucial thing, and not I should say the crucial thing, one of the ways you must think of this as saying is that if A and M are related like this, then if you take any x in M, then you look at x divided by norm x. That is going to be the unit ball of M. So you can approximate that by, in fact, on bounded sets, the SOT, the strong operator topology is actually metrizable. So this will say that if you take an x in M, look at x over norm x, then you can actually find a sequence an in A such that an converges to x over norm x. And an and all have norm less than or equal to 1. You multiply by norm x, then you'll have a sequence where everything has norm less than or equal to norm x, which converges to x. So I'll put that as a corollary. X in M implies equals A closure SOT as before. That means A is a star algebra, implies there exists a sequence an in A so that norm an less than or equal to norm x and an converges to x SOT. So you can actually get down to sequences in SOT by cleverly applying Kaplanski, if you are in that situation. Okay, and here are some more useful corollaries. Let one in M contained in B of H be a star algebra. Then the following are equivalent. 1 M is a one-dimensional algebra. i.e. WOT close or SOT close or whatever. One-dimensional algebra in B of H, you are already given this is a unital star algebra. It just means that it is WOT close. 2 M is sigma weakly closed. This is because okay, we'll put this because of Kaplanski density. So why is this true? Because if
on unit for sigma weak and weak, what is the masses?
But why is M sigma weakly closed? Okay, so let me write the full thing down. The unit ball of M is sigma weakly compact. Okay, so sigma weak was the topology that came from that the closure of the finite those wxy's those linear functions. So we know that the sigma weak topology and the weak WOT agree on bounded sets. So if it's WOT closed, it's certainly sigma weakly closed, because sigma weak convergence implies WOT convergence. So 1 implies 2 is obvious, right? This is obvious. Because because sigma weak convergence implies WOT convergence. So that WOT closed implies sigma weakly closed. Okay, M is sigma weakly closed, then this M1 is nothing but the unit ball of B of H intersect with M. And we've shown that B of H is a dual space. And so the intersection of sigma weakly compact set and no, that is what I should have said. If M is sigma weakly closed, why does it follow that M1 is
Sigma topology is basically weak star topology. As you have identified, K is not star. So unit ball is
but no, it is a weak star topology for B of H. We define the sigma weak topology as the weak star topology on B of H when restricted to M.
And if it is sigma weak, you can identify M lower star also with it.
No, I'm saying the unit ball of B of H is sigma weakly compact.
Yes.
If I intersect it with M, which is sigma weakly closed, I will have a closed subset of a compact set, which must be compact. Consequently, this is compact. And if this is compact, then now I use Kaplansky. Suppose I have an algebra A such that its unit ball is compact. Then this will show that its unit ball must be SOD dense in or WOD dense in the one-dimensional algebra it generates. See what does, okay, see 3 implies 1 is what you want to prove, right? So first I appeal to one-dimensional density theorem. So sorry, let's write for the moment A rather than M. So I say suppose 1 in A contained in B of H is star algebra. Such that A, the unit bond of A is WOT compact. See, on bounded sets, all the sigma weak and weak topologies are the same. Okay, then one-dimensional density will tell me that if I take the strong closure, is a one-dimensional algebra. That is, A is SOD, is a star algebra which is SOD dense in a one-dimensional algebra M. So by what we proved here, if M is A closure SOT, then you can find a sequence of, if I take any X in M, I can find of norm less than or equal to 1. This will show that the unit balls of A and M must be the same. See, while Kaplansky will tell me that A1 is SOD dense, or which is the same as WOT dense in M1. But A1 is WOT compact. So that means that A1 must be equal to M1. No, A1 compact, WOT compact implies A1 equal to M1. If you have two vector spaces which have the same unit ball, then the vector spaces must be the same. That means A has to be equal to M. That means this A must already have been a one-dimensional algebra. This okay. See, there are a couple of okay, I don't know if you know this or need this. Okay, so let me take this with one observation. There is a fact about C-star algebras that okay, let me digress with that. Suppose A, B are C-star algebras. So I want to state two things that happen in the C star and in the W star categories, which are kind of nice, which don't usually happen in lot of cases when you're looking at infinite dimensional spaces. Okay, so the theorem I want to say is that so suppose pi mapping A to B is a star homomorphism. And let's assume they all have units and unitary. We only look at homomorphism that preserve the one, send the one of this to the one of that. Okay. Then norm pi equals 1. And in fact, more is true. Not just this, and in fact, pi of A is a C star subalgebra of B. See, the only non-trivial statement about the second that is being made, pi is a star homomorphism, so it is clearly a star subalgebra. What is not clear is that why is it closed? Why is it norm closed? In general, if you have a mapping between Banach spaces, the image of under a bounded operator, the image of Banach space need not be closed. So there is something very non-trivial that you are getting for free here. That any star's homomorphism of unitary algebra automatically has a star closed range. And the same, so the same thing will hold in the one Neumann case. That if you have a morphism between two one Neumann algebras, that means I have a sigma weakly continuous mapping from A to B, where A and B are one Neumann algebras. Then it will be true that it has norm 1 and the image will be a one Neumann subalgebra of B. That means it is sigma weakly closed, which is again saying something quite strong and
weak operator topology continuous.
Huh?
We map weak operator topology continuous. What is the morphism?
sigma weak, yeah. See, in general, when you're looking at one Neumann algebras, I said there's this abstract definition which is to think of one Neumann algebras as C-star algebras with a pre-dual. And the topology, the morphisms in that category are star homomorphisms which are sigma weakly continuous. And the previous corollary that I gave you gives the secret away. If I have a sigma weakly continuous map from M to N, look at the unit ball of M. There is sigma weakly compact, so the image is going to be compact. But the image will be exactly the unit ball of N, in a unit ball of the image, because the pi has norm 1. Okay, so let's see why this is true. Actually, this requires a little work, but so here's a sketch of a proof. In the first case, let us assume that let us assume A is 1, 1, pi is 1, 1. You don't really need that. So this is for proving this part actually. So if I forget this statement, then let me prove it properly. If I only want that the norm of pi is 1, so I need to show that it is enough to prove that norm of pi x squared equals norm of pi x star x. Actually pi x star pi x. But because pi is a star homomorphism, that is the same as norm of pi of x star x. So it is enough to show that so it is enough to prove that norm of pi a less than equal to norm a for all self-adjoint A. But if A is self-adjoint, what you know is that the norm pi A is also self-adjoint. Both sides are self-adjoint, and for self-adjoint operators, the norm is the same as the spectral radius. So whether this is contained in less than equal to spectral radius of A is what you are asking. But it will be enough if I can show that the spectrum of pi of A is contained in the spectrum of A. If I know that, then clearly the spectral radius will be smaller. But this is obvious. So I'm saying pi is a homomorphism, it sends 1 to 1. So if x is invertible, then pi x must be invertible. Or if pi x is not invertible, then x is not invertible. If pi x minus lambda is not invertible, then x minus lambda is not invertible. Okay. So this shows this assertion. For this one will do a little more work. So let's see use some other one-Neumann trick to do this in the general case. Yeah, since I've said this, and the other part, since I'm going to have to kind of look at it, and I'd probably make a goof of it. So let me do this, at least do this properly, and then we'll go to the one-Neumann case next time. So to prove this assertion that the image is norm closed, so what one does is, so one considers two cases. So case one, you assume that pi is 1, 1. Okay. Then what I see is that pi inverse, which will make, no, but I don't know that there is no. No, I can't do it.
Pi is 1, 1, pi will be isometric.
Huh?
Pi is 1, 1 is then
pi is 1, yeah. So then you want to say that, you want to conclude that, you want to prove that this implies pi is an isometry. That means you want to say that, again by the same kind of C-star identity kind of trick, it is enough to show that it is isometric on self-adjoint elements, for which it is enough to show that the spectrum of A and the spectrum of pi A are the same for self-adjoint A. So what you have proved is that spectrum of pi A is contained in spectrum of A. You know this. So suppose this inclusion is proper. So you have one compact set and a proper compact subset of that. That means you can find a function in a continuous function on spectrum of A so that f is not identically 0, but f on the smaller set is 0, identically 0. So it's just unison or whatever. So proper compact subset, then you can find a set which is 0 in the neighborhood of this, but not identically 0. But then you'll have a problem, because if you look at pi of f of a, that will be f of pi of a by continuity. This is true for polynomials p, and so by continuity, since polynomials are dense in all continuous functions, this is true for all functions. But then you look at the spectrum of the spectrum of this so see, I want to say that this is 0, but this is not 0. No. I want to, no, this is f of
Left side not 0.
no. I want to say f of a is not 0, but pi of f of a is 0.
Since the right side is 0.
Since f is not identically 0, f of a is not 0.
But pi belongs to spec of pi. So f of pi equals to 0.
Right side is 0.
Right side is 0, so left side is 0.
Right side is 0, so left side is 0.
So f is 0.
So this means pi of f of a is 0, but f of a is not 0. That contradicted the assumption that pi was 1 to 1. So one proves in the injective case like this. In the general case, there is something that we haven't discussed at all, but that is a separate thing. So one shows that in general case, for general pi, look at the kernel of pi. What do you expect this to be? If you have a morphism and if you look at kernel, then you expect it to be some kind of an ideal or something like that, right? So this will be a star-closed ideal. And in general, things which are kernels are those things for which the quotients will make sense in that category. So in fact, you have to prove that the facts are for any such ideal J. If you look at A mod J, you learned that in Banach space also. Where the Banach space in J is norm-closed, then the image is going to be a Banach space. It's going to be complete space. So there's going to be a norm-closed space. Here this is a natural adjoint because J is star-closed. And you only need to prove that this is a C-star algebra. That is the natural norm on this quotient space is in fact a C star norm. So that requires some work which I don't want to go into here. And so you prove that A mod J is actually a C star algebra, and then you appeal to this case. If from A to pi A you have a mapping inside B, and then you have A mod J, which is the kernel. If you have mapping pi, then there will be a star homomorphism pi bar like this, which will make this thing commute. And pi bar is going to be injective. So what you know, pi bar is going to be isometric. And so its unit ball will be closed. I don't even know how to say it. Its image itself is complete. And so its image is the same as the image of pi. That is why the image of pi is closed. Okay, so we'll do the one-Hammond case next time.